Determine all intervals of concave up or concave down and determine the coordinates of all inflection points, including cliffs, for the function f of x equals 1 over x squared plus 27. The first thing to do is find the domain. So f of x equals 1 over x squared plus 27, which has a denominator, and the domain requires that the denominator cannot equal to 0. So x squared plus 27 cannot equal 0. We can solve for x by subtracting 27 from both sides. So x squared cannot equal to negative 27. And we can then take the square root of both sides. So x cannot equal, it'll give a plus or minus the square root of negative 27. Since it's an even root of a negative number, it's not a real number. So x cannot equal plus or minus a non-real number. Therefore, there's no real numbers that x cannot equal. The numbers that can't equal happen to not be real. So x can be any real number. So the domain will be all real numbers, or negative infinity to positive infinity. The next thing to do is find all candidate numbers. We will need the second derivative for this. We will start with the first derivative. F of x is 1 over x squared plus 27. One option is the quotient rule, but the numerator does not have any x's, so it's better to rewrite this by bringing the denominator up to a negative power. It will be x squared plus 27 in the numerator as a negative 1 power, and the 1 will sit in front of it. It's implied, so we don't need to write it. Now the first derivative is just a power rule. So f prime of x equals, bring the power down, leave the inside alone, subtract 1 from the power, minus 1 minus another 1 is minus 2, and then multiply by the derivative of the inside to complete the chain rule. We can move the 2 and the x out front with the negative 1. Negative 1 times 2 is negative 2, and then x, and then x squared plus 27 to the negative 2. One option is to move that x squared plus 27 to the negative 2 down to the denominator, make it positive 2, and then use the quotient rule. Another option is leave it as is and take the product rule directly from here. Let's just take the product rule. F double prime of x equals the derivative of the first, derivative of minus 2x will be minus 2, times the second left alone, x squared plus 27, so minus 2, plus the first left alone, plus or minus is a minus, so minus 2x, times the derivative of the second, which is a power rule, will bring the power down, minus 2, leave the inside alone, x squared plus 27, subtract 1 from the power, and that would be the minus 3, and then multiply by the derivative of the inside to complete the chain rule. The first term we'll leave as is. It's a minus 2 x squared plus 27 to the minus 2. The second term, we can collect all the constants together. There's a negative 2, a negative 2, and a positive 2. Negative 2 times negative 2 is positive 4, times the positive 2 will be positive 8. So we have a positive 8. There is an x and another x, so that will be x squared. And then there's an x squared plus 27 to minus 3. We want the second derivative to be a single fraction, all powers positive, and fully factored. One option is to take these negative powers, move to the denominators to become positive powers of each of the terms, and then find a common denominator, combine them together to make the single fraction, and then factor the result. Another option is to factor it as is, which is usually quicker and easier. For the coefficients, there is a common factor between 2 and 8 of 2, so we can factor a 2 out. And there's also a common factor of x squared plus 27 to the lowest power. The lowest power is the -3. -3 is lower than -2 by being more negative. So we can factor out an x squared plus 27 to the -3 power. Factoring these out will give the result of taking out the 2, this will become a -1, this will become a 4. Factoring out the x squared plus 27 to the -3 power. Factoring is division. Division is subtraction of exponents. We will be subtracting a -3, which is adding a 3 to each of the exponents. For the first exponent, adding a 3, -2 plus 3 will be a 1 power. So we'll have the entire thing to the first power, which is just x squared plus 27, and then times the -1 that sits in front of it. For the second term, adding a 3 to the exponent, we have a -3 plus 3, which will be to the power of 0. And anything to the power of 0 is a 1, so that entire thing will be a 1. So we just have the 4 and the x squared. So we have a -1 times x squared plus 27, and then plus 4x squared. A -1 times x squared plus 27 to the first power, and then plus a 4x squared. So f double prime of x equals, we have a 2 times x squared plus 27 to the -3 power. Inside the square brackets, we can distribute the -1 in, which will give -x squared minus 27. And then plus 4x squared. So leaving the first part of the expression alone. In the square brackets, we can combine like terms. I'm going to turn it into parentheses now. We have a -1x squared and a positive 4x squared. -1 plus 4 is 3, so 3x squared. And there's also a minus 27. There's a common factor in there of 3. We can factor it out. It can move all the way to the front with the 2. 2 times 3 will be a 6. We'll leave the x squared plus 27 alone. It's the -3 power. Factoring out that 3, we'll leave behind an x squared minus 9. We want to fully factor the second derivative. We have a difference of squares left over, x squared minus 9, which can factor further. So we have 6 times x squared plus 27 to the -3 power. And x plus 3 and x minus 3 it'll factor into. We want all powers to be positive, so we can move that -3 power to the denominator to become positive 3. And the second derivative will be, in the numerator there will be a 6, there will be an x plus 3, there will be an x minus 3. All of those were to a positive power. And the x squared plus 27 will move to the denominator to become a positive 3 power. So we have the second derivative written as a single fraction. All powers are positive, and it is fully factored. So we can now set the numerator equal to 0 and the denominator equal to 0 and solve for all x's, starting with the numerator. 6 times x plus 3 times x minus 3 equals 0. It's already factored. X plus 3 equals 0 tells us x equals -3, and x minus 3 equals 0 tells us x equals positive 3. And now working with the denominator, x squared plus 27 cubed equals 0. We can take the cubed root of both sides, because the cubed root and cubed power cancel each other out. So then x squared plus 27 equals the cubed root of 0. The root of 0 is equal to 0 for any root. We can now subtract 27 from both sides, so x squared equals negative 27, and take the square root of both sides, so x equals plus or minus the square root of negative 27. That is, again, an even root of a negative number, which is plus or minus not a real number. We now check to see which of these are in the domain. Well, the not real number will not be in the domain because the domain is made up of real numbers, so we don't include that. But x equals negative 3 and x equals positive 3 are both real numbers, so they will be in the domain. We can now draw a domain line, a line representing the domain. It has no left end because it starts at negative infinity. It has no right end because it ends at positive infinity. We can now put any candidate numbers on here. We have x equals negative 3 and x equals positive 3 in order. The negative 3 will come first, and then the positive 3, which splits the domain interval into 3 separate intervals. We can pick a test value in each of these intervals. The first interval, negative infinity to negative 3, we can pick negative 10. The next interval, from negative 3 to positive 3, we can pick 0. The next interval, positive 3 to positive infinity, we can pick positive 10. We can now test the concavity in each of these intervals by plugging the test values into the second derivative. We don't care about the value of the second derivative, just whether it is positive or negative. So the best place to plug in is the fully factored version. That's this one here. Now a couple of things about this. In the denominator, there is an x squared. So if x is positive or negative or even 0, squaring it will never be negative. And then adding that result to 27 will guarantee that it's positive, and then raised to a 3 power, positive to a 3 power will be positive. So the entire denominator is positive. Also, the 6 in the numerator is also positive. And therefore, those do not affect the sign of the second derivative, and it will be determined whether it is positive or negative solely by the x plus 3 and the x minus 3. Starting with the test value of negative 10 plugged in there, negative 10 plus 3 is a negative number. Negative 10 minus 3 is a negative number. Negative times negative is positive. We have a positive second derivative that corresponds to concave up. Plugging 0 in, we have 0 plus 3, which is a positive number, 0 minus 3, which is a negative number. Positive times negative is negative. We have a negative second derivative. This corresponds to concave down. Plugging a positive 10 in, 10 plus 3 is a positive number. 10 minus 3 is a positive number. Positive times positive is positive. We have a positive second derivative. This corresponds to concave up. So we have concave up happening from negative infinity up to negative 3, and then union, because it is happening again from positive 3 up to positive infinity. We have concave down happening from negative 3 to positive 3. Right at the candidate number of x equals negative 3, we do have the concavity changing from concave up to concave down. So x equals negative 3 will be an inflection point. It has an x-coordinate of negative 3. It has a corresponding y-coordinate that can be found by plugging the negative 3 back into the original function. So y equals f of negative 3, which is 1 over negative 3 squared plus 27, which is 1 over negative squared is positive, 3 squared is 9, so 9 plus 27, which is 1 over 36. right at the candidate number of x equals positive 3, we again have the concavity changing from concave down to concave up. So x equals positive 3 is also an inflection point. It has an x-coordinate of 3. It has a corresponding y-coordinate that can be found by plugging the x-coordinate back into the original function. So y would equal f of 3, which is 1 over 3 squared plus 27. 3 squared is 9. And it looks like it'll have the same y-coordinate, 1 over 36. So we have two intervals of concave up, one interval of concave down, and two inflection points, negative 3, 1 over 36, and positive 3, 1 over 36.